we have a long break after the first lesson, right? So I hope you still remember something. Okay, so let's see where we stopped last time. Let's go to. Okay, so in our first lesson, we have talked about the characteristic of simulation. Okay, and the simulation study that we learn in this course will be discrete event, will be stochastic, which means random, will be dynamic, which means change with time. Okay, and then we talk about the steps we need to carry out in a simulation study. Okay, so I guess you already forget these tests more or less. So let us review the step we need to do in the simulation study through an example. Okay. So I take an example of a convenience store. Okay, so like Circle K is an example of a convenience store. So I think all of you are familiar with this. Okay, so let's say we want to conduct a simulation study of a convenience store. Okay, so we will follow this step in a simulation study by starting with the problem and objective identification. Okay, the reasons that we need to be clear about our problem and our objective is because it will affect a lot on the way we come up with our simulation model. We may create a very detailed simulation model, or we may simplify many information. Okay. Okay, hold on. I forget to record this one, so let me record this. Okay. All right. So we assume that in this case, our convenience store have a new competitor. Okay, so we would like to see what we can improve for our store, and then we may want to make some change in our store, but we want to do it through simulation. Okay. Do you still remember the advantage of simulation? One of the advantages of simulation, we can play with the simulation model without intervene the real system operation, right? So we try to use simulation to evaluate the performance of this convenience store, and then we make some change in the simulation to see what can we improve. Okay, so let's say that's our objective. Now, the second step in the simulation study would be understanding the system that we study. Okay, so by understanding the system, we mean that we have to know the logic involved in that system. Okay, and all of the data related to that logic. Okay, so when we talk about the logic, we mean we will come up with a conceptual model. Okay, so this is the conceptual model. Okay. We need to create a conceptual model to describe the logic of this system. Okay, and then we also need to collect all the relevant data along with that logic. Okay, so these two things will help us to understand the system we want to simulate. Right, so now how's the conceptual model look like in our example? So usually in simulation, one way of doing simulation is that in order to create a conceptual model, we will try to think of the process that carry on in the system, and we usually start with something enter the system, okay, and how it goes through the system, and then it go out the system. So that is usually the way we a way that we come up with the conceptual model. So let's say in our convenience store, what will enter our system, right? So we will start with the customer. Okay, naturally we will think of a customer. The customer will enter our system and then spend some time there and then go out of the system. So we will think our system logic in that way. All right. So now, is there anyone here familiar with a convenience store? So I would like to invite a student. Okay. So can you describe for us the process? Okay, when starting with the customer and the convenience store, and then what happened next inside the system until the customer go out the convenience store. Can you think of the process? All right. So okay, so let's see. Okay, let me invite someone. Okay, Kim Ngọc, are you there?
Yes, I'm here.
Okay, Ngọc, great. Okay, so Ngọc, have you ever been a convenience store before?
Yes, I have been to a convenience store before.
All right, Ngọc, great. So can you think of can you, let's say you are a customer, so can you tell us the process that the customer enter the convenience store? So what will they do?
When a customer enter a convenience store, they will search for their product, like they demand.
Okay, so they will walk around, right?
What
Okay, walk around the store, look for the product they want. Okay, and then
If they cannot find the product, they might ask the staff.
mm-hmm. Okay, so if they cannot find the product, they will ask the staff. Okay, and then
Uh, if they find the product, they will check the price and
go on, go on. You
and
are right, Ngọc, go on.
they
Yeah,
will
do a
check
good
it out
job.
at the cashier
Mm-hmm. And they go to the cashier.
to check to to purchase the product.
Mm-hmm. Okay, they pay for the product, and then
And then they go home.
okay, then they go out. So the convenience store that you mentioned, does it have a place so that the customer can stay there to eat noodle, for example?
Uh, yes, they may. Uh, uh, most is the convenience store they have a place for customer to stay there and eat food.
Mm-hmm. Okay, so they after they pay the product, they have the option to stay there if they want to stay there to eat, or if not, if not they can leave, right? So we have another two situation after the cashier rang up.
Yes.
Okay, great. So basically, that's the way that the convenience store uh, operate. Okay, and we will put that on the paper. Okay, so that's what we call conceptual model. Right. So okay, so I have a slide here to describe the process that very similar to what our friend just shared. Okay, so we will put all of the things that you say here on the paper like this one, and we call this one conceptual model. Okay, so you see we start with the customer arrive. Okay, we start from here. Now, depends on our objective. Let's say we are not so much interested in like a different type of customer, like we know that there's some customer who buy a lot of things. Some customer usually just like the students, the pupil, like the children, they just walk around and see what are interesting, but they rarely buy nothing. Okay, or some customer just buy exactly what they need. All right, just a few things. So if our objective is to monitor different type of customer, then we may in our data collection you may distinguish different types of customer. If not, then you can maybe you can just ignore this one, okay, and go straightly from customer arrive into the shopping area. Now, again, just now Ngọc say very interesting details like whether the customer can find the product they want or not. If they cannot find, then they can ask the staff. Again, if let's say our objective is to see the occurrence of this situation, because let's say if we are managers and we are concerned on the situation, we are concerned on whether the customer can easily find the product they want or not. So in our data collection, we will pay attention on that situation. Okay, we will record how many times that the customer have to ask the staff for information. Okay, but if let's say we are not focused on that one, yeah, we just want to know in general how the customers, how long the customers spend time in our convenience store. Then we can ignore that information, okay, and we can ignore that detail in our logic. All right. So let's say to make it simple, we just start from the customer arrive and go to the shopping areas, and again here you may look into details like how many eyes there are in the shopping area. If you are interested in like the route of the customer wandering in the convenience store, then you have to put like how many eyes here. If not, you also can ignore the information. All right, so depends a lot on our objective. Okay, so after they spend some time in the shopping area, and then they decide whether they want to buy things or not. So we have a decision node here. Okay, usually in simulation we use this symbol for decision node. Okay, so we have two cases here. If the customer don't buy anything, then they just leave. Okay, they just leave, go out of our system. If they want to buy something, then they have to proceed to the checkout area, the cashier. Okay. So again here, we would see like how many cashiers we have here, how many checkout lane we have here. Okay, and then again after they pay, we have another situation here whether they want to eat or not. Okay, so if they don't want to eat, then we just go out again. So we join with this one, just go out. And if they want to eat, again, they have to look around for the chairs, for the seat. Okay, so we have another situation here whether there's enough seat in the store or not. So if not, then they also have to leave. All right. Yes, they will stay there for eating, and after eating, they will leave. Okay. So this all of this flow chart we call it conceptual model. Okay, so this one will help us to understand how the system operates, and depends on our objective, we may skip some uh, details, some information in our conceptual model. All right. Now, this one alone doesn't help us to. It's not enough for us to simulate the real system. So, as I told you, we still need to collect the data, go along with all of the step here. So, what kind of data we need to collect here? You look at here. You look at this project. What kind of data we need to collect here? Anyone want to answer? What kind of data we need to collect if you look at the conceptual model like this? Arrival rate and service rate as element. Okay, so we start from here. The customer arrive. Okay, so we need to know like how frequent they arrive. Okay, so like there's not so many customers arrive in the morning, and there are more customers arrive around 11 and so on. So we need to collect the data related to the customer arrive. Okay, and okay, let's say we don't pay attention here. If we are interested here, we also need to know like the percentage of different type of customer here. Okay, they go around for shopping area. Okay, so do you think that we need to collect the time that they spend in the shopping area? Do you think so? Yeah. Okay. Well, I think that we also need that one. Okay, if we are interested in like how long the customer spend in our store, so we also need to get the data related to time here. Okay, and then we have a decision here whether the customer want to buy or not. So here we also need to collect the data this node. Okay, so let's say we collect the data from 10 o'clock to 12 o'clock, and in that time slot we observe 50 customers. So we need to know like the percentage um, of that 50 customer, how many of them decide to buy something and how many of them buy nothing. All right, in order to simulate that one, so we also need this data at this node. Okay, and then go to the checkout errors. This is what you mentioned here, the service rate or the service time. So they will have to queue here. So we need to know how long it takes to make the payment here. Okay, we call it service time. Okay, and so maybe there's a case where if there are two cashiers, then we need to collect the service time of either of both two cashiers because maybe one is slow, one is fast, for example. All right. Okay, so and then at this one again, where the customer decide to stay for eating a go. So we also need the data here. Okay, so like we need to know the percentage of customer want to eat at the convenience store and the percentage that not. Okay, all right, and then at this node, whether enough chairs or not. Okay. In order to simulate this one, you also need to collect the data. How many occurrence, how many times that the customer encounter not enough chairs. Okay, in the time slot that we observe right? We need to get that information to put in our simulation model as well. Okay, and then if they if they're successful to get a seat and stay there for eating, and we need to know how long, usually how long, right, they spend for eating. Okay, because it will affect the available chairs. If they stay there for too long, then the next customer will not have a seat. Okay, so this one is also very important, right? So by plotting the conceptual model like this one and collecting the data along with each step in this conceptual model, we more or less understand the system, and now we are ready to translate our conceptual model and the data into the computer. Okay, all right, so we finished the step conceptualize model and the data collection. Now, all right, so let's go to the model translation. Okay, now we go to this step, model translation. The model translation here means we will translate the conceptual model and the data we collect into the computer. And in our case, we will use Arena software to help us to do that. So, all right, so if you look at if you use Arena, okay, your computer model or your simulation model on a computer will look like this. In Arena, okay, it looks like quite complicated, right? So actually it's very simple. Now I go back to the conceptual model here. I will explain to you in a very simple way how we do it in a computer. So Arena software will provide us many modules to display common logic that we will encounter in any system. Okay, so usually it will have the module that we always have to use at the beginning is the create module. Okay, so it will have a create module. The module name create. Okay, so so you just pick up the module name create on the software panel and drag it into a simulation model. So this create module will help us to create the customer. Okay, the simulation language we will learn later. We call it entity. Anything that enter the system, go through the system, spend some time in the system, and go out the system, we call it entity. Entity. Okay, I'm sorry, it's quite ugly. Entity. Okay, so in our case, the entity would be the customer. So this create module will help us to create the entity of the customer that enter into the system. And in this create module, we need to tell Arena the arrival rate of our customer, like how fast, how slow, for example. Okay, now just now you tell me that we need to know about the arrival rate of the customer. Okay, so we will learn about the arrival rate later. But think of the way you collect the data related to the customer arrival. How do we collect the arrival of the customer? So let's say I choose to observe the convenience store from 10 to 12 in the morning. Okay, so I will, let's say, for example, I will stand at the door and I will record like every 5 minutes how many customers arrive. Okay, so sometimes, so let's say I will do like this one, 10 at 10 to 10 5, and I say there are 2 customers arrive. Okay, and then next from 10 5 to 10 5 minutes later, and I see only 1 customer arrive, and the next one, I'm sorry, 15, the next 15 minutes late, next time I have 0, for example. So until I do that until 12 p.m. Okay, so I will record different arrival rate of the customer along the time. So now I will need to put all of this information into this create module of arena. So later you will learn how to put it in arena. There are basically a few ways, but the key point here is everything is random. You see, sometimes every 5 minutes we have 2, sometimes we have 10, sometimes we have none customer. So everything is random here. So the way we have to modelize this randomness in simulation. Okay, and we will use the statistic that we learned long time ago, right, to describe this randomness of the customer arrival. Okay, so we will learn it in another lesson to see how we simulate the randomness here in arena. Okay, all right, so okay, so after the arena will generate the customer for us according to the arrival rate that we want here. Then let's say they go to the shopping area and spend some time here. So in arena, it also have a very common module. We call it process module. Okay, the process module look like this one. It's the triangular shape. Call it process. All right, so in this process module, you have to tell arena how long the entity will spend time here, and does it need any resource to serve it or not, and how many resource that it needs, and how many resource that the system has. So you can tell all the information in this module. Okay, it will appear the window and you have to key in the information in that window. All right, so for this case, let's say in the shopping area, the customer just spend time. We assume that they don't need any help here, so we don't put any resources. We just tell that, well, the time that the customer spend here. So again, the data that we collect regarding the time the customer spend in the system also very random. Okay, so let's say we have 50 customer. The first customer only spend 2 minutes. Next customer spend 50 minutes, and so on. So should we take the average or what? Well, again, we will need to use statistics, all right, to describe the randomness of the time the customer spend in this system. Okay, just like the arrival rate here, right? So we will learn it another lesson, and that one we call input modeling, how we model the randomness of our input data. Okay, all right, and next the customer will go to the checkout area. So here we have a decision here. Okay, so Arena have another module, very common module called design module. Okay, design module. So after the customer go to spend some time the shopping area, all right. So we can use a design module here. Okay, so in this design module, Arena will let you define the probability here. Okay, so let's say you can define like 60% will go to the checkout area, 40% will go out by nothing. So you can define the percentage here in the design module of Arena. Okay, so and then they go to the checkout area. So can anyone tell me which module we can use to describe the checkout area? Which model in Arena that we can use to describe the checkout area here? Which one? I just told you we have the create module, okay, to create. Thanks on, great, you follow me. We can use the process module, okay. So for the checkout area, again, we can use the process module, just like in the shopping area. But now, in the process module that we use for the checkout area, we need to define the resource because we need the cashier here, right? So now, how many cashier we need to serve one customer? Probably one, right? We only need one cashier to serve one customer. So we will define that, wow, we need one. Our resource, we will give a name for our resource. Let's say it's, we give any name that you like. So we give it the name cashier. And we define that we only need one cashier. However, how many cashiers we have? So in this example, we have two cashiers. All right, so we would have the resource required and the resource capacity. Right, so we only need one resource, but we have two cashiers. All right, so we will define everything in the process module. Okay, all right, and after that, after payment, and then we have the customer either stay or go. We have here. So which module we will use in Arena here? Anyone? Which module we use it? Is it too obvious? All right, we will use design module here, all right? So again, we will use design module, right, to tell Arena how many percentage the customer stay for eating and how many percentage will go. All right, so so in this example, actually, we only need to use a very basic modules in Arena, and we already can simulate the operation of the convenience store. Okay, and even though it looks complicated, like this picture. Okay, even though it looks complicated like this one, but actually you only need to use a few models, the basic model that I described to you. All right, now remember that, again, we remember the objective of our simulation model. You want to create a simulation model in order to evaluate the performance of our convenience store, and then we want to play some experimentation on our simulation model. And now we already have a simulation model. Should we let the software run it? Can we play experiment on it now or not? Okay, so we look at our simulation study step again. So we here experimentation design. But before, in between the model translation, where we have a computer model here, to the experimentation, we have another two steps. Okay, verification and validation. All right. So what happened here is that we already have a simulation model in our computer, but are we sure that this computerized model is a correct one or not? All right. We only can use it. We can only use its result, or we can do experimentation on it when it is correct one. Right. So we have to make sure that the computerized model here, all right, is right. So when we say that it's correct one, we mean that it really reflects the system that we want to study. Okay, so in order to assure that our simulation model really the same, okay, reflect the real thing, we have to check. And the checking step includes two steps. The first step we call verification. So we go back to this one. Let's say we start here. We start with the real system. We have the real system outside here. The real one outside here. And then we have another one on the paper. We call it conceptual model. Okay, and then we have a data. And then we have another one on the computer. So firstly, we need to make sure that the one that we put on the computer really reflect the conceptual model that we put on the paper. You will see sometimes that this is our idea that the customer need to go from this stage to another stage, but somehow when we translate it into the computer, it doesn't run the way we want. So it really doesn't reflect the conceptual model that we have on the paper, let's say. Okay, so we have to make sure the conceptual model is the exact one that we have on the computer. Okay, and that step we call verification. Okay. So it's also so when you already put well, you already finished creating the computer model, and right now you have the run button. So you press that run button. When you press that run button, the run button here, there are two situations. Okay, the first situation is there's an error pop up, and it's very likely happen for every beginner. Okay, and tell you that well you have some error, or you fail to put certain information in certain module, or you forget to connect certain module. Okay, so that one we call debug. Right, just like you do programming, you have to debug, let the program run. So it's also included in the verification step. After you debug it, okay, and you press the run button again, okay, it's run. Okay, but still you have to make sure that it run the way you want. The way you want means the conceptual models that you already created. Okay. So you will practice that, you will learn that in the lab. Okay, while we do different example, and you will try to figure out how to know whether your computer model is really the conceptual that you want. And actually it's really a skill. Okay, we have to practice a lot. Okay, now So after we sure somehow that the computer model is the conceptual model that we want. So we done the step verification. Now we go to the next question, which is even more important. That is the simulation model that we have. Is it related? Does it reflect the real system or not? Can you distinguish the two things? We have two things here. One is the real system, and another one is the conceptual model. This is the real one, and this is the conceptual one. The fact that we have a simulation model that reflects the conceptual one doesn't mean that it reflects the real one. But our ultimate purpose is reflecting the real one. So again, we need to do one more step. We call it validation. Okay. The validation step is to compare the simulation model on our computer with the real one. All right. So, so how to do that? We will have another lesson related to validation. Okay, how to validate our model. But remember, this is our ultimate purpose. Our simulation model on a computer must reflect the real one. Is it possible that it reflects the conceptual model, but it doesn't reflect the real one? Is it possible, everyone? Do you think it's possible? Why not? Okay, let's say if you come up with the wrong conceptual model. Okay, somehow you miss very important information of the real system, and so your conceptual model is wrong. Then you translate into the computer. You do the verification, it's all right. The computer model describes the conceptual model very well, but your conceptual model is wrong. So at the end, your computer model doesn't reflect the real one, so you cannot use it. Okay, so it's possible that the simulation model reflects the conceptual model, but doesn't reflect the real one. So you still need to do the validation step. Okay. Now, one question for you to ponder. Why do we need to do the verification before we do the validation? Why don't we go straight away from, let's say, why don't we, okay. Why don't we go directly from the computer model to validation? But why we need to go to the first step, verification, and then validation? Why we need to do two steps? Anyone wonder about that? Okay, you think about that, alright? You think about that. Why we need to do two steps? Our ultimate purpose is to make sure that our simulation model reflect the real one. But we need to do two steps. The first one is verification and then validation. Think about it. Alright, now, so when you do validation, when we compare our simulation model with the real one, there are two situations. The first one, find that when we compare with the real system, let's say we choose certain parameters. Let's say we want to look at the waiting time of the customer, for example. We go to the convenience store and we collect the waiting time of the customer, and this is what we get from the real one. And you compare with the waiting time of the customer that you get from the simulation. You compare these two figures, and we will have two scenarios. first scenarios, they are very similar. So we can say that we have a validate model. Means that our simulation model reflect the real system. And then we can go to the next step. We can use it, we can analyze the result, we can do the experimentation. The second scenario is it's totally different, all right? The waiting time of the of the real one is very different with the waiting time we get from the simulation study. Okay, so in this case, we have to check what's wrong here, what we have to fix here, why our simulation model doesn't look like the real one. Okay, so what should we check here, everyone? We have to go back to our conceptual, right? Right, we have to look at whether our conceptual model correct or not. Do we miss any information here? And we have to check the data collection here. Right, sometimes our data collect is not correct. So we have to check these two. And then we go again, the loop we have to fix it in the computer, and then we verify and then validate again. So it's really an iterative process. Okay, iterative process until we can create a model that reflect the real one. We call it a valid model. Valid model. Then we can use it. Okay. Another point here, when we do the validation, is the randomness of the result. So you know that let's say the simulation that we are dealing with, the system that we are dealing with have a lot of randomness there. Like the customer arrive is random. The time the customer spend in the shopping areas is random. The service time is also random. Like some customer take like 1 minute for checkout, some customer take 5 minutes for checkout. Alright, so everything is random. So because our input is random, so the output is also random. Alright, so let's say if you look at the waiting time of the customer, for example, okay, so if you run simulation, you get the average waiting time is 5 minutes. And then when you go to the real convenience store, you get the average waiting time is 6 minutes. So the question is, 5 minutes the same as 6 minutes, or they are really different? We can say that is similar because we look at the average, because everything is random. So if we do more than this one, maybe not 5 but maybe 5.5 for example, all right, or we may say it's very different. 5 is very different from 6. All right, so in order to answer whether 5 is the same with 6 or not, we will need to use a hypothesis testing here, and it will fall in the lesson of validation here. Okay, so the answer is not straightforward here. We will have another lesson for this one. All right. Okay, so all right, so let's assume that everything goes smoothly and we have a valid model at the end, and it's ready to use this valid simulation model. Now we can look at the output that we get from the simulation. Okay. So when we run Arena, it will give us the option to choose how many times we want to run the simulation. We want to run it 1 time, 2 times, 3 times, 7 times. How many times we want to run? We call it triplication. And Arena will collect the statistic from the number of runs that we run and give us the average, the maximum and the minimum. Okay, so so let's say we are interested in the number of customer waiting on the queue. Arena will provide that statistic for us. Okay, so it will provide for us the queue length of lane 1, the queue length of lane 2, what is the maximum number, the minimum number, the average number. If we are interested in the waiting time of the customer, it also can provide us that statistic. Okay, and from that statistic, we make our comments. Okay, whether this is high or low, compared to our benchmark, compared to our competitor. Okay, we also can collect the statistic on the percentage of the customer stay or leave in our simulation model. Okay, so for example, in this one we have 32% customer decide to stay and 68% customer decide to leave from the simulation. Okay, so let's say we want to increase the percentage of customer want to stay here. All right, and we want, let's see what we can do in our simulation model. All right, so we will do the experimentation. Okay, so currently we have two cashier, two lanes for queuing here. So you may add one more checkout lane. Okay, and see what happens. Will it help to reduce the waiting time significantly or not? Okay, and we do it on simulation. It doesn't affect anything on the real system. All right, we just change in the process module of the cashier. We increase the number of resources from 2 to 3. That's simple. Okay. Or more complicated, like we can adjust the working schedule of the cashier. So let's say from 8 to 10 a.m. we see that the customer arrival is not much, so we can schedule only one cashier in that time slot, and from 10 to 12 p.m. we will schedule two cashiers. Okay, so you have an option to do scheduling for the resource in the arena. Right, you can try that one. And let's say in the self-service area, we also can increase the number of seats. So seats is also a resource. Okay, so in let's say the customer choose to choose to stay for eating, then we also can use another process module there where we define the time that the customer spend for eating and also the number of seats, right, that we have in the convenience store. All right, we can do that with the process model, and then we can change the sitting number in the convenience store. All right, so so that's all. All right, that's basically the steps that you will need to carry out for any simulation study of any system. Okay, and again, it's an iterative process. So throughout our course, we will have different lessons that focus on different steps in this simulation study. Okay. So we will have a lesson to learn how to translate the data that we collect into the computer. Right, so how do we simulate the randomness of our input data using statistics? Okay, we will have a lesson that teaches how to do verification and validation. Okay, and then we will have a lesson to analyze the result. Okay, because the result in simulation is not quite straightforward. the input is random, so the output is random. Again, we will need to use our statistic knowledge to analyze the output result. Okay, and then we will learn how to do experiments in a simulation. Okay, so basically that's our course. Any questions so far? Do you have any question? All right, so if you have no question, then we can play a quick review, okay, to see if you get the main point of this lesson or not, and then we take a break. All right, so I want you to go to the Kahoot website now, and then we will play this review game. I will put the link for you here. Okay. Okay, can everyone, you go to this Kahoot website and we will play the review game. Okay, or you can key in the game pin here. Okay, so when you put your name, please key in your student ID. Okay, put your student ID only. Right, I will record it as like a check-in attendance. While you can understand like that, or actually I want to take it as a bonus for you for the process. Okay, so key in your student ID for my record when you play the game. Okay, can we try it now? So after you finish the game, then we can take a 10 minutes break. Okay, right, finish the game and you just take a break. We are at 2:20 now, so you do it for 5 minutes. It's 2:25. Then we will back on 2:45. Okay, we back on 2:45. So okay, everyone. Alright, so I leave you with the game. Alright, so this is our problem. Sorry if you can read it or not. Okay, we want to find x that gives us the minimum value of fx. So to solve this problem, we can solve it analytically, like the one that we have learned long time ago in high school. Okay, by taking derivative of f. Okay, we can take the derivative of f. Okay. All right, and put it equal to 0, and then we will find out x. So this x will give us the minimum value of our f, and this is an exact solution. Okay, this one is an exact solution. So I should put this one will be an exact solution. The analytical solution will give an exact solution. Okay, another way to solve this problem is that we will try different value of x. Okay, so you can try x equal to 0, and then we check what is the value of f. Okay, we try different value of x. Right, we try x equal to 0, and we find what is the value of f. All right, then we try another value of x. Okay, let's say 1, and we got another value of f. And similarly, so depends on the time we have, we can try a number value of x. And then among the number value of x that we try, we can find out which one that gives us the smallest value of f. All right, so let's say we try 0, 1, 2, 3 until 10. And then we find out that f x equal to 1 give us the smallest value of f, then our answer will be 1. That is in the case you are lucky. We try x equal to 0, 1, 2, 3 to 10. But let's say if we try x from 2 to 10, for example, then our answer will be different. Our answer will not be 1, but let's say 2, for example. So the answer that we give in that case is just a near exact solution. It's not exact solution, it's just a near optimal one in the region that we try. So this one we will call numerical solution. All right, numerical solution. So the simulation model that we do in here is indeed a mathematical model. It does have the equation to describe the relationship, the parameters in our system, but the way that we come up with the result will based on numerical solution. If you try different values of the input and give us different value of the output, and then it will take what is the average of the value of the output. Okay, it doesn't solve the mathematical question analytically like when you learn in operation research, for example. But even in operation research, later if you take the course scheduling, you will learn different algorithm. Okay, and you call that heuristic one. So the heuristic one is also a type of numerical solution. It helps you to find the near optimum solution. It's not exact solution, but because the problem is too complicated, so we cannot solve it analytically, but we have to try. We have to find a way to search for a near optimal solution. Okay, so again, our simulation model is a mathematical model, and we will solve it. We will find the answer, the output by numerical solution, numerical method. We try different value and then get the average of it. Okay, so that is the answer for the first question. Okay, all right, so let's see the next difficult question. Okay, so all right, it's very good. Actually, we only have two difficult questions. What are not the characteristics of simulation? All right, so we have four options here. Simulation doesn't disrupt the real system operation. This is true. Okay, this is true. So we don't choose it. This is correct. It helps decision making. Yes, it's correct because we can try different scenario and then we make decision after that. So this one also correct. Now the third answer, simulation can provide optimal solution. All right, this is wrong because for simulation again, let's say when you do the experimentation on the simulation, you have to think of what kind of experiment you want to try. Okay, what kind of answer you want to test. The simulation doesn't give you the optimal answer. You have to think of certain solution in your mind and then you test it in the simulation and to see whether it is good or not. Okay, it's unlike the mathematical model that you learn in OR1. When you solve OR1, all right, you have like you want to minimize or maximize the objective function, and then you solve the problem with all the constraint, and your solution does give you the maximum or minimum objective. So in that case, you got an optimal solution. But for simulation itself, it doesn't give you an optimal solution. You have to think of solution yourself and you test it in the simulation. Okay? All right. So that the second question that most of us misunderstand. Now let me see. Okay, maybe we try one more. One more. The third one. Okay. Which one is not in the correct order? So let me see. Alright, so we have 90 students choose the correct one. You have to do modern translation and then okay, what is the correct order here? The correct order should be, let's look at the first one. We have model conceptualization. We do data collection and then we translate the model into the computer. So this is the correct order. Okay. The second one, we do the modern translation and then we do validation and then verification. This is wrong. You have to do verification first before you do validation. Okay, so just now I asked you the question why we need to do two steps and I asked you to think about that, remember? So you have to do the first step, verification first. Verification means you check your computer model. Is it really the logic that you want, the logic in the conceptual model that you want or not? After you do verification, then you do validation. Okay, so this one is the verification is before the validation. The validation is the final step where you compare the computer model with the real system. Okay, so you choose B is right because this is the wrong order. And next we have verification, validation, and doing experiment. This is correct. Okay, all right, good. Okay, so I think the rest you are doing fine with other questions. So we can carry on with the new lesson today. So let me open the slide. Okay, so our lesson today is based on our textbook, chapter 2, the author of Jerry Banks. I have already posted on the textbooks that we use in this course, so you can review it on yourself, the book, with the ebook. All right, now the purpose of our lesson today is to illustrate to you some key concepts in the simulations. And before we do it with the software, okay, with more complicated system, we will use a manual way, so-called manual way, by creating a spreadsheet. And in this manual way, because it's slow enough, it's simple enough, it helps us to understand the key concepts in simulation easier. Okay. So the key concepts that we will look at here is the randomness of the event. All right, how do we represent that randomness, that uncertainty of the event of the system that we want to simulate? And then any simulation study need to have a purpose, and usually that purpose is to evaluate the system performance. So how do we look at the system performance? What kind of descriptive statistic that we can use to look at the system performance? Okay. We say that it should be a descriptive statistic because we are not dealing with a fixed number. We are talking about uncertainty and random. So everything we should play with statistics. So the performance that we look at here, the figure that we look at here to evaluate the performance is a descriptive statistic. Okay, and we also get familiar with the way of thinking of model instead of what are the input, what are the output, the response, events, so on. Okay, now so on the examples that we study here, you will look at what are the input of the system. Okay, what are the output of the system? The output, we also have use another name, we call it response. Okay, because uh, we call it response because when we change the input, the output will change. It will respond to the changing of the input. So sometimes people call it the output, the performance output. Some people call it response. So they have the same meaning. Okay, and the way we observe the relation between the input and the output is by using a table. Okay, so we will try different value of the input and then we will calculate the output value, the response value, and we will do it many times. Okay, each time we call it a repetition. So each repetition we will give a different value of the input and then we see how the response change. Okay, everything is random, so that's why we don't do it one time. We have to do it many times, and every time is different. Okay, so this is the way we will do the simulation manually. We call it using a spreadsheet, and we totally can do it in Excel. Okay, the examples that we are taking here is very common. Like the first one is the queuing system. This one we see everywhere, right? Almost any system we have something enter and then make a queue and wait to serve, whether it's a production or whether it is a service one. Okay. The other example we will take is the inventory one, the inventory system. This one is important to those who study logistic one as well as ISE. And the third example is related to the reliability issues. Okay, in the factory. Okay, this is more related to the IE students. Okay. Right. Okay, now, so we start with the first system, queuing system. Okay. It will look like this one. Okay, we have entity. Remember the terminology I introduced to you just now, the entity, like the customer. Okay, they are from somewhere, we don't know, we call it a population. Okay, and they join into our system. Okay, they make a queue here, wait to be served, and after they serve, they go out and join back to the population. All right, this is principle of the queuing system. So now, how do you describe a queuing system? Let's say we want to simulate a queuing system. We have to understand the system, right? So how to describe queuing system, everyone? How to describe queuing system? Anyone want to try? Either way, your participation is taken note for bonus. Okay, so let's say we have someone arrive from the population, right, to join into the system. So we will have the arrival, all right, the arrival rate of whatever entity to our system. Okay, so we need that to describe our system. Okay, whether it's fast or slow, whether it's constant or it change with time. All right, so we have to look at the arrival rate into our queuing system. All right, now the second one, when when it go to our system, it will queue. Right, that's the code name, the queue system, queuing system. So it's have to wait. Now, if you think of a supermarket, right, you will have a lot of cashier, and each cashier will have one queue, right? But let's say if you go to a convenience store, for example, it may have only one cashier, but it can arrange the customer into different queue, for example. All right, so it's like this one. I'm sorry. You may have many server. You say two server, but you only have one queue. So which server free first? The queue, the next customer will join that server. Right? So you may have one queue for one server, or many servers share one queue. So that one we call a queuing discipline. Okay, we call it a queuing discipline. All right, so to describe a queuing system, you have to tell what is the queuing discipline in the system. Okay, one queue, two queue, how many queues? All right, next, we have the server. Okay, so how to describe the servers here? You have to tell how many servers you have, and then how fast or how slow the server serve the entity. Okay, so we can have the service time. Right. So all of these together is describing the queuing system. Okay, the arrival rate, the queuing discipline, and the service time, and the number of servers. All right. Now the next question: how do you evaluate the performance of a queuing system? How do you evaluate the performance of a queuing system? Nhật Minh. Nhật Minh, are you there? You
Yes,
want
I'm here.
to evaluate a performance of the queuing system. How do you, what parameter will you look at?
Sorry, I have no idea.
Oh, okay, I made it simple. Let's say you go to a restaurant. How do you tell that this restaurant is good or bad?
I think it will depend on many factors like the cost of that restaurant or the meal. Yes, like that.
The cost, the meal, okay. All right, so that is for the restaurant. So you can concern on the quality of the meal, the quality of service. How about, do you concern about the waiting time?
Yes, of course.
Okay, you were concerned about waiting time. So when we talk about a restaurant, so you talk about the food, okay, whether it delicious or not. All right, but let's say if you go to a cinema, then you not talk about the food anymore, but the movie. But all the queuing system is common in the sense that the waiting time.
Yes.
All right, so yeah, we have an answer here. How long we have to wait? All right, so let's say you go to the hospital, you spend a very long time there, but we have two type of times. One is waiting time, and another time we, we see the doctor. So okay, you can mute it. All right. So we want to spend as long as we can with the doctor, but we don't want to wait for so long. All right. So all the QA system has one thing in common. We will look at the average time we wait on the queue. Okay, waiting for the service, or we want to look at the queue length. If the queue is very short, it's good, right? But if the queue is too long, it's not good. All right. So that's the most common performance parameters that we usually look at in a queuing system. All right. So now we go to a specific example. Okay. We look at the most simple example of a queuing system where we only have one queue and one server. Okay, one queue is one server. We call it single channel queue. We only have one queue and then one server only. All right. And we have, this is our population. Now, so firstly, we look at the arrival rate of our customers. Okay, so these are the information we get. The customer arrive at random times from 1 to 8 minutes apart with equal probability of occurrence. So this is the information we have. So the time between arrival of the customer can be varied from 1 to 8 minutes. Sometimes it's only 1 minute. Like the first customer, after 1 minute, we got another customer. Sometimes it may be 5 minutes. Like the first customer arrived and after that 5 minutes, then we have a second customer. So the time between, we call it time between arrival. It varies. And we assume that from our observation of the real system, we collect 8 situations. The time between arrival can be 1, 2, 3, 4, 5, 6, 7, 8. And then based on the data we collect, we find out that the probability for each case is about 12.5%. We assume this is the data we get from the real system, and we come up with this result. We need to simulate this characteristic of the arrival rate. All right. So if we put the cumulative probability is it will become 1 at the end, right? So 1, 0.125. And we have time between arrival 2 minutes. If you add in, it will be 0.250, and we have 8 scenarios. In total, we have 100%. This is a cumulative probability. Okay, now the next information we can get is the service time of this grocery store. This one we also can collect from the real system. So we also measure the service time for each customer that we observe, and we find out that the service time may vary from 1 to 6 minutes. Okay, so again, we also count like how many customers have to spend 1 minute with the server, how many customers spend 2 minutes with the cashier, for example, and then we come up with the probability. Okay, so we have 10% the service time is only 1 minute, 20% the service time is 20 minutes, and so on. So if we sum up, we take the cumulative probability, the end will be 100%. Okay? Alright, so this is the characteristic of the grocery store, and we have a very particular number we get from the real system. Okay, we try to simulate this system with this characteristic of arrival rate with a single channel queue. The queuing discipline is only 1 queue. Okay, with the service time have this probability. All right. Now, again, our simulation must have a purpose. We want to evaluate the performance of this system. So let's say we want to answer what is the average waiting time of the customer in this queuing system. How long they spend in this grocery, and let's say we are also interested in what is the idle time of the server. Are they very free or not? Okay, so if you are the manager, you will be interested in these parameters. Okay, so these are our simulation purpose. So we will do it by hand, and we will use this simulation table. Okay, so we will try about 20 customers. Okay, 20 customers. I'm sorry. 20 customer here. Okay, so all right, so we want to know what is the time customers spend in the system. Okay, what is the time the customer have to wait? What is the idle time the server for each customer? Each customer. Okay, and for each customer, we will have to try different value of the arrival time and the service time. Okay, so these two can be considered our input, and these three can be considered our output, our response. We will vary the input value and see how it changes in the output. All right. Now the problem is the arrival time of the customer and the service time is vary according to this rule that we collected. Okay, so how do we simulate this probability of arrival time and service time for these 20 customers? Okay, for sure we will vary the service time and the arrival time of the customer, but we need to vary in a way that it follow this rule, and this rule we get it from the real system. You get it? Okay, so how do we simulate the randomness or the probability of the arrival time and the service time in this case? Okay, so So let's see some of the techniques that people usually use to simulate probability of an event. Okay, so now let's say okay, so let's say I'm saying that well, according to my historical data, 50% of the students will fail the simulation course. All right, so the event that fail or pass the simulation course is 50%. So let's say I take any random student, okay, and I want to simulate this 50% probability. How can I simulate it? All right. So one way, if you want to simulate an event that have a 50% probability, then you may think of using a coin, right? So what is the probability that we have a head, or what is the probability that we have a tail? It's 50-50, right? Okay, so if we say the head is pass and the tail is fail. So if I get on the head, I say pass, and if we get the tail, I say fail. So I somehow using the coin to simulate a 50% probability of an event. Okay, or you want to go or not go, and like it's the same to you. So you use a coin to make decision. Okay, so it's 50% probability. You can use the coin to simulate that. Let's say if you use well, a dice. We want to cast the dice. How many faces in the dice we have? How many faces on the dice? How many? 1, 2, 3, 4, 5, 6, right? So what is the probability that I can get number 1 here? What is the probability that I can get number 1? If I cast the dice here, 1/6, yes. So what is the probability that I get 3? Also 1/6, okay. So if you want to simulate a probability of like 1/6 event, okay, so 1/6 is how many? Is it 0.125, is it? Okay, then you can use a dice, okay, and then assign each phase for a certain decision, for example. So this one way. Now, if you have more situations, right, this one you have only 6 situations, and for the coins you only have 2 situations, 2 scenarios. But if you have more than that, then people usually use random number. So if you use your calculator, you will see most of your calculator will have a function that give you that help you to generate random number. Okay, so you can take your calculator right now and try. Right, so you press the random number, and it will give you a number which is completely random. So when we talk about random number, it means that the probability for that number appear is the same with other number. Right, it has uniform distribution. So if I ask you to give me a random number, then maybe you have a tendency to give me a number that you like. All right, but if you use a calculator, if you have an algorithm inside that will give you a number which is completely random, there's no trend, there's no pattern there. The occurrence, the probability of occurrence of any number is exactly the same. Okay, so that's what we call random number. So besides of the calculator, people also have the table where they record many random number here. So whenever you pick up any number here on this table, they have the same probability of occurrence. Okay? All right, so these are some way that people use to try to simulate the probability of the event. Okay, now we go back to our example. We want to simulate, let's say, the time between arrival with this probability for this value. Okay, if we only have 6 value, you can have a dice. You can use a dice to simulate this one. But now we have 8 values. So I will introduce you a technique, right, to use random number to simulate this kind of probability. All right, so okay, we look at the time between arrivals. Okay, we have 8 values here, and the probability we get is here. This is the cumulative probability. So now I will use my calculator to help me generate a random digit. Okay, so and this is my rule. If the random digit that the calculator give me fall from 1 to 5, okay, then I will assign that customer the time between arrival is 1 minute. Okay, now I try the next customer. If the random digit that the calculator give me fall from 1 to 6 to 250, then I will assign the time between the arrival is 2 minutes. Okay, so I will try like that. So I will have like from 1, all right, to 0. So actually it's 999 and the maximum is 0, 1000. We type is 0 here. Okay, so depends on the random digit that I get from the calculator. I will assign the time between arrival accordingly. Okay, so if I get a random digit from the calculator from 501 to 625, I will assign the time between arrival 5 minutes. Okay, now can anyone see the relationship between the random digit assignment here with the probability we have here? You will get a bonus if you answer this question. Can anyone see the rule here? What is the relation between the random digit assignment we have here with the probability here? The upper bar is the cumulative. Yes. And what else do you see? Okay, so let me ask a question. What is the probability that you can get any random digit from 1 to 125? The random digit is based on the scale of 1000, that's right. Okay, Roman, excellent. 12.5%. Even yet you guess it. Why? Why you come up with 12.5%? The question is, what is the probability that we can get any number from 1 to 125? That's right. there are 125 numbers out of 1000, so the probability would be 125 over 1000. Okay, so similar questions. What is the probability that we can get any number from 126 to 250? 126 to 250. What is the probability that we can get any number from 126 to 250? The same probability, because we also have 125 numbers from 126 to 250. All right, so that's the answer here. That's the relation that we have here. By using the random digits, okay, we somehow can simulate the probability that we want here for the time between arrivals. Okay, so we will use the same technique for the service time. So we look at this table. Our service time can be 1 to 6. Okay, now we look at the probability here. The probability here is not the same. Like the service time is 1 minute, we have 10%. 2 minutes, we have 20%. 3 minutes, we have 30%. If they are the same, then we actually can use the dice, right? We can cast the dice and we get the service time if the probability are all the same. But here we have different probability. Okay, so in this case, what can we do? Okay, again, we generate a cumulative probability here. And we have 10%, 30%, 60%. So now I will use 2-digit numbers from 1 to 99, from 0 to 99 actually. Okay, so if I get any random digit from 1 to 10, okay, I will assign the service time 1 minute. If I get any random digit from 11 to 30, I will assign the service time 2 minutes, and so on. Again, can you see the relation between the random digit assignment we use with the probability here? Okay. All right, so we see what is the probability that we can get any number from 1 to 10 out of 100 numbers. Exactly 10%, right? What is the probability we can get any number from 11 to 30? We have 100 numbers, and from 11 to 30 we have 20 numbers. So the probability would be 20%. All right. And how about 31 to 60? We have 30 numbers from 31 to 60, and out of 100 number, we would have 30% probability. All right, so again, we will use random digit to simulate our service time with this probability. Okay, we can start now. Okay, so we start with the first customer. All right, the first customer arrived. So, okay, so we don't generate the time for the first customer here because, okay, we consider that the first customer start at time 0. Okay, so we don't need to simulate the time between arrival for the first customer. Okay, now the second customer, when they will arrive, we will use our calculator to generate a random number. So let's say we get a random digit 913. All right, we go back to the distribution of the time between arrival that we just discussed. Okay, 913. 913 is in this range from 876 to 1000 here. So we will assign the time between arrival between the first and the second customer is 8 minutes. Okay, so it is 8 minutes. Okay, all right. The third customer, how long it takes after for the third customer arrive after the second customer? We don't know. We will simulate. We use our calculator to generate a random digit, and let's say we get 727. All right. We look at our random digit assignment. 727 is in this range. 727. So it's corresponding to the time between arrival 6 minutes. Okay, so we got 6 minutes. The third customer arrived 6 minutes after the second customer. So by doing like this one, we somehow can generate the time between arrival of the customer randomly, but follow the probability that we want. All right, students? Okay, now we will do the same for the service time for every customer. So the first customer, how long it takes to serve him? We don't know. We will generate a random digit using our calculator. We got 84. Okay, we check our random digit assignment. 84 is here. So we will assign it 4 minutes. Okay, so the first customer will take 4 minutes. All right, similarly, the second customer, we generate a random digit. We got 10. And we look at this table, 10 is here. So the service time would be 1 minute for the second customer. All right, we do like that for 20 customers. We will generate service time completely random, but follow the probability that we want here. All right, so that's how we modeling the probability of our input. Now we put everything in our simulation table. Okay, for customer number 1 to customer number 20. Okay, and each of them we have the arrival time and we have service time for each of them. Can you calculate how long each of them have to wait? How long each of them stay in the system? And whether the server idle or not for each case? It's easy. Let's say the first customer arrived at time 0 and then have 4 minutes service time. So other column it just help us to calculate easier. So the time service begin will be 0, and because this is the first customer, so they don't have to wait. It's 0. The waiting time is 0. The time service end will be 4 minutes, right? Because it had 4 minutes here, so the service will end 4 minutes. And the first customer will spend 4 minutes in this system. The time the server idle is 0. No, it's not free. It have to serve the customer. Now we go to the second customer. The second customer arrive after 8 minutes. All right, we generate from our table previously, so we know that the next customer arrive after 8 minutes. So the arrival time would be minute 8, right? The first customer at 0, so the second customer will arrive at minute 8. Now the service time for the second customer we generate randomly is 1 minute. So the service time will start at 8. Okay, at 8. Now, do the second customer have to wait, everyone? Do they have to wait? Do they have to wait? The second customer, do they have to wait? The first customer leave at minute 4. The second customer arrived at minute 8. So there's no waiting time here, right? All right, so we can put 0 here, no waiting time. And when it's end, we have the service begin at minute 8. Service time is 1 minute, so it's end at 9. Okay, and how long the first customer arrive? Spend in the system? Only 1 minute for service because don't have to wait. All right. All right, and you can calculate what is the idle time of the server. How do we come up with these 4 minutes? How can we come up with these 4 minutes? The first customer leave the system at minute 4. The second customer arrived at 8 minutes, so the server are free from minute 4 to minute 8, so we can calculate it's 4. Right? So we can do like that manually for every customer. Right? We will see when the first customer arrive, when they leave, and what time the next customer arrive. Do they have to wait? If they have to wait, how long they have to wait? As long as we have the arrival time and the service time, then we can calculate the rest for each customer. Okay, any questions so far? Okay, good. So now, what next? So what? After we do everything for 20 customers, what's next? Remember, we want to answer what is the average waiting time of each customer. All right, that is a statistic. We call it a statistic. Average is a statistic. So the data we have here is 20 customers. We have the waiting time of 20 customers here. So we can take the average waiting time of each 20 customers. Okay. All right, this is just a sum. You have to divide it by 20, then we got the average. Or let's say we want to know what is the average time the customer spend in the system. We have the time the customer spend in the system for each 20 customer here. So you can again take the average of these 20 customer. Okay. Or you want to know what is the average idle time of the server. We have 20 situations here. We can take the average. Right. So the next slide gives us the formula to calculate the average waiting time, average service time, and so on. It's very basic one. But it highlights the point that this is the way we use simulation to come up with an answer. Okay, and this is again a numerical method. We try the value of different input and we see the output, and then we take the average here. Okay, everyone, any questions so far? This is a simple system, so we completely can do it manually like this by hand, or you can do by Excel. Okay, by apply certain rules here, the relationship between different columns. Okay, so the points that we want to highlight here is the need of simulate the random of the input. Okay. Later you will learn different ways to simulate it. Okay, but it's one way. Okay, and how we use the descriptive statistic to describe the performance of the system. Right, we use numerical solution here, method here. All right, and we get the statistic like the average of waiting time, average of time in system, and so on to evaluate the performance of the system. Okay, and you see actually the relationship between this column is actually mathematical, right? Whether it is plus or minus, whatever, there's a relationship between these parameters. So actually it's a mathematical model. Okay, so I think we have to stop here, and we will continue with other examples next week. Is there any point that you don't understand today? All right. If not, then we stop here. We are just on Tuesday, so almost you still have a long week, right? So all the best to you with other online lessons. Okay, see you class. Bye bye.